Hi, Professor. This is Zefan, and
And this is Rendale.
so today we are presenting the our E238 final project. We are working on voltage control boost converter operating in discontinuous mode. So here we have a quick agenda. So first we'll talk about the what's voltage mode control and what's current mode control. Next we'll talk about um, disc discontinuous conduction mode and continuous conduction mode. Then we'll present some reference design with different compensation topologies and what they are using in the industry. And lastly, we will briefly go through our project design. So the voltage mode and current mode control.
So in voltage mode control, we use a single feedback loop compared to a reference voltage, and we use that to vary either the duty cycle or the input voltage. For our case, we will be modifying the duty cycle. And switching the duty ratio allows us to change the voltage across the inductor, and hence the inductor current, thus changing the output voltage. Whereas compared to current controlled mode, we are controlling both the voltage and the current. The signal is generated and compared to some voltage, a reference voltage, and then we use that error signal to generate a controlling current. That controlling current will then control the inductor current. We use these instead of duty cycle if we want to have different characteristics. They both have the pros and cons, which will be discussed in the next slide. Whereas in voltage mode control, obviously it's easy to design. We just create one compensator and we just connect the duty cycle to the output. And we have high noise tolerance. So any variability within both the input or the output can easily be nullified from the compensator due to its stability. The cons are there is low system response time. So it may take a while for any changes in the output to make it through the compensator to have reasonable effect, as well as degraded reliability and stability when we're working with many loads on the output. The circuits in the compensator have to be specifically sized to work properly, and this can have significant impact on output matching. Whereas in current mode control, it does have high stability on the feedback loop. There is a rapid response time because we're affecting the current directly, but the cons are that it is more complicated and the compensation network is in a single phase. And it is generally the preferred method, but for our cases, we are going to use a voltage mode control because that is the necessary requirements. So other than voltage mode and current mode, we also have DCM versus CCM. So for our project, we are working in DCM, discontinuous conduction mode. Discontinuous conduction mode happens whenever the inductor current reaches zero or the capacitor voltage reaches zero before the end of the switching frequency. Thus, any assumptions we have about the circuit in continuous conduction mode cannot be held anymore. And this causes complications in both the transfer function as well as the output voltage. We can't rely on the same system equations to both design the compensator as well as get a reasonable output voltage at a specific frequency. And so obviously in DC converters and rectifiers, we use single quadrant switches. And so in those single quadrant switches, we actually do often run in discontinuous conduction mode, unless you're using full quadrant switches. It's the only way you can get around this problem. So it is a regular phenomenon that you do have to run into when working with DC-DC converters. One obvious case where discontinuous conduction mode will occur is when either our components are we are limited by the size of our components, and so that our capacitors can't be large enough or inductors can't be large enough, or we're operating at light load or, as you can say, small current. And sometimes we do need to use DCM at all operations because that is easier to work with depending on the components. On the next slide. And so comparing to DCM and CCM for the boost converter, in DCM, the inductor current or another way, the capacitor voltage is fully discharged before the end of the switching cycle. And that does cause the voltage gain and design parameters to be dependent on various aspects of the circuit, such as the capacitor and resistor voltages of the load, rather than be uniquely dependent on the duty cycle. This does cause much larger ripple currents as well as much larger voltage swings at the output. So that might be con for any devices on the output side, which may be voltage dependent. But it is, the pros are that it is easier to make stable because by being in DCM means there is no instability, as well as you can use smaller component sizes, as well as it is great for designs without load because we do have such wide switches at the voltage. Compared to continuous conduction mode, the current will not discharge to zero, as well as the capacitor will not discharge to zero. And so the gain is independent of the load. It only depends on the duty cycle. And it is more efficient. There is not as much power loss as in DCM. And there's less ringing on the inputs and outputs. But it is more ideal for constant loads as it is stable at really any load.
So next, I will talk about reference designs. So for the conversation network, there are three topologies that we can use. We have type 1 to 3 compensators topologies. So here first part here we will talk about the type 1 compensator. We can use for the type 1 compensator or type 2, type 3, we can use either a traditional operational amplifier or we can use operational transconductance amplifier. So with the traditional op-amp, it requires a local feedback to make it stable. So you can, on the right-hand side, you can see there's local feedback at the output of the op-amp and connect it back to the negative input of the op-amp. So under the DC conditions, both input are virtually at the same voltage level, thanks to the golden rule of the op-amp. So for the OTA, so the local feedback loop is not necessary. We have the output voltage of the op-amp is equal to the output current multiplied by the capacitor C1 impedance. So in this case, we will actually need to include the GM of the op-amp and the R4, which is the voltage divider resistance into the transfer function. Compared to the traditional op-amp, we do not need that. So next, I'm going to talk about what's out there in the design. So this is Taas instrument design on one of their application notes. So here they are using OTA in the boost converter design. So with this, at the bottom you can see there's one transfer function and there's a right-hand pole 0 frequency function. So based on the function, we can tell that at heavy loads, the right-hand pole 0 frequency is the lowest. So that means the phase delay is the greatest. So in this case, it will be a little bit difficult to control the converter. But compared to the light loads, the right-hand pole zero frequency is higher, so the converter is easier to control, same as the inductor. So with large value of inductor, right-hand pole zero moves to the lower frequency, so it's more difficult to control. And then reducing the values of inductor makes the converter easier to control. So you can also see the heavy load and light load gain and phase change in the graph here. So next one, this will be our type 2 compensator. So compared to type 1 compensator, we are adding one more capacitor and resistor. So for the traditional op-amp, we do have the extra capacitor and resistor into the feedback loop. So because with the type 2 compensator, there's always a negative phase, so it cannot be used to improve the phase of the power stage. For this reason, we cannot use this for the voltage mode control in continuous conduction mode, where there is a large phase drop just after the resonant frequency. So with the OTA, so you can see on the right hand side there's a schematic of the OTA. So we are adding the extra capacitor and a resistor to parallel to the capacitor at the output of the op-amp. So next is this is presented in one of the paper. So I have it referred in the reference page. We can see that this is voltage mode control plus current mode control. So I'm highlighting the voltage mode control here, that he's using the traditional op-amp method. So here we have the peak current in the inductor current in the DCM is given by this equation: I peak equal to V in divided by L multiplied by duty cycle and the switching time. So decreasing the inductance can cause the maximum current to increase, and the switching losses of the power losses of the switching can become dominant. So that means you have more losses. So for the control system, right-hand pole zero appears at high frequency, and then the converter can be approximated to a single pole system, which simplifies the frequency compensation. So next, this is our reference 3 design. So I will not go in detail for this design, because for the reason that the transfer function derivation is very similar to type 2. So the principle remains the same as the type 2 method. Next, the one unique thing about the type 3 compensator is this one is used to compensate the voltage mode boost converter operating in continuous conduction mode. So lastly, I'm going to briefly talk about our project design. It's not completed yet, but we have a rough idea. We have a draft schematic here. So our design spec will be V in 20 volt, V out 30 volt, and we will set the switching frequency at 200 kilohertz and reference voltage is 5 volt. So we are using the type 2 topologies for our compensation network. Okay, so this is the reference. If you are interested in this, you can go to the links and read the papers. Thank you.